Hi everyone, and welcome back to the MCAT A series of lectures in physics. In these last two videos, we will cover our final topic, namely atomic and nuclear physics. I will begin this video by introducing what is known as the photoelectric effect. This phenomenon is what causes electrons to be emitted from the surface of a material when light is incident upon it. I will then look again at the Bohr model of the atom, this time with regards to what happens when light is incident upon atoms. I'm sure you know these things already from chemistry, but just to be sure, I will also recap what is meant by both atomic number and atomic weight. Likewise, I will look at neutrons, protons, and isotopes in more detail. Various nuclear forces will then be considered and what role they play in binding energy. A large portion of this video will focus on what is known as radioactive decay, which is the spontaneous decay of an unstable nucleus. Finally, I shall finish this first video in this two-video topic by describing an instrument that is used to determine the mass-to-charge ratio of a particular ion. This is done by using what is known as a mass spectrometer. As I just mentioned, when light is incident upon certain materials, it is possible for that light to cause electrons to be emitted from the surface of that material. This is known as the photoelectric effect, and whether this happens is dependent upon both the frequency of the light and the particular material. In terms of the latter criteria, it is typically metals in which the photoelectric effect occurs. Why does the frequency of the light matter? Well, the energy of a light wave is directly proportional to the frequency. The higher the frequency of light, the more energy that light wave has. Since electrons are in some way chemically bound to the atoms on the surface of the material, if the light wave is to remove that electron from that material, it must have enough energy to overcome this chemical bind. The minimum energy a light wave must have if it is to emit electrons from this material, from this metal, is known as the work function of that metal. Therefore, naturally, the work function will be different for different metals. It is more difficult to remove electrons from one metal compared to another metal. Therefore, the work function is said to be an intrinsic property of that particular metal. Of course, it is probably clear now why the photoelectric effect typically occurs in only metals. Metals, of course, have free electrons, which are easier to remove compared to electrons in other materials. We can also ask, what is the resulting kinetic energy of those ejected electrons? To work this out, all we need to do is consider conservation of energy. As I already stated, the energy of a light wave is directly proportional to its frequency. As I've written here, that proportionality is Planck's constant h. Planck's constant is a very small number, and it is roughly equal to 6.6 multiplied by 10 to the minus 34 joule seconds. Joule seconds because, if we rearrange this equation, Planck's constant is equal to E over F. It is equal to joule per hertz. However, since a hertz was defined as a per second, this is a joule per second, or a joule second. How does this help us? Well, initially, before the interaction, all of the energy is contained within this light wave. What happens to this energy after the electron is ejected? Well, some of that energy has gone into overcoming the work function. Some of that energy has actually been used in order to eject the electron at all. Any remaining energy is then used by the electron to move. In other words, the remaining energy is the electron's kinetic energy. Therefore, before the interaction, the energy was purely in the wave, it was purely this hf. And after the interaction, some of that energy went into the work function, and the rest of that energy went into the electron's kinetic energy. Therefore, according to conservation of energy, that is, the energy before is equal to the energy after, we have that hf is equal to the work function capital W plus the electron's kinetic energy capital K. Rearranging this for what we are interested in, The kinetic energy of the electron is equal to hf minus w. Here I've written K max because, depending upon how that light wave is incident on the metal, for example what angle it hits it at, and other things, for example non-conservative forces taking energy away, hf minus w should be considered the maximum possible kinetic energy for the electrons. It is not necessarily what the kinetic energy of the electron actually is. Therefore, based on this logic, if the energy associated with the light wave, this hf, actually exactly equals the work function of the metal, then this is considered to be the energy at which the electrons are just about ejected. They are hypothetically ejected with zero kinetic energy. Therefore, as well as talking about a minimum energy needed to eject electrons, we can also talk about a minimum frequency. Again, as the energy of the light wave is equal to hf, and also at this minimum frequency, the energy is simply equal to the work function, the work function can then be considered to be defined as this same h multiplied by that minimum frequency. That is, the work function capital W is equal to Planck's constant h multiplied by this minimum frequency f. Here I've written f sub capital T as this minimum frequency is typically known as the threshold frequency. As long as the light wave has a frequency higher than the threshold frequency, when it is incident upon a metal, it will cause electrons to be ejected. Again, on the MCAT, you may need to use this in a more complicated setting. For example, remember, the speed of a wave is related to its frequency and wavelength by v is equal to f multiplied by lambda. Therefore, in the MCAT, you may instead be told the wavelength of the light. You may also be told that that light wave is traveling through air, and therefore the speed can simply be assumed to be the speed of light in a vacuum, 3 multiplied by 10 to the 8 meters per second, and you may need to use that equation first to work out the frequency, and then plug it into this equation. Also again, remember why I stated that the photoelectric effect only typically happens in metals. In a metal, there is a relatively weak bond between valence electrons and the atom. Therefore, electrons in metals are typically easy to remove compared to other materials. However, in nature, the photoelectric effect does indeed occur in the absence of metals. For example, when a light wave hits the chloroplast of a plant cell, it also causes the ejection of electrons. These electrons are then used to produce glucose. Therefore, we see that although the photoelectric effect appears to be something that only happens in certain specific situations, it in fact occurs a lot in nature. Next, I already recapped in a previous video the Bohr model of the atom. That is, that the center of the atom contains the nucleus, which in itself contains protons and neutrons. Neutrons are neutrally charged, protons are positively charged, and to have the atom overall neutral, there are also negatively charged particles known as electrons that orbit the nucleus. If you have already covered the chemistry portion of the MCAT, you will also already know what I'm about to describe, namely what happens when light is incident upon an atom in such a model. According to the theory, each electron cannot exist at any distance from the nucleus. It can only exist at certain distances. Therefore, the electrons are said to exist in discrete orbits. Also, the further away the orbit is from the nucleus, the greater the electron energy. Overall, this means that if an electron wants to, what we say, jump from one electron orbit into another, there must be some exchange of energy. This is typically done using light waves. For example, an electron can go from a high energy orbit to a low energy orbit by emitting a light wave. Emitting a light wave causes a loss of energy, thereby forcing that electron to jump to an orbit of lower energy. Conversely, when an electron absorbs a light wave, it jumps from a low energy orbit into a high energy orbit. Remember, however, the energy of a light wave is determined by its frequency, E is equal to hf. As the electrons exist in discrete orbits, if an electron is to jump from one orbit into another, the energy and therefore the frequency of that light wave must be a particular precise value. Therefore, even if the photon contains only slightly less energy needed for an electron to jump to the next energy level, it won't move. It won't move because its only option is to either stay there or jump to the next level. It cannot exist at any space in between. If it does not have enough energy to get to the next level, it will remain where it is. Here on the left, I've drawn what is known as atomic absorption. This is what happens when a light wave is absorbed by an electron, thereby giving it enough energy to jump to the next energy level. Atomic emission, on the other hand, is the release of a light wave when an electron jumps down to a lower energy orbit. One phenomenon based on this idea of absorption and emission of light is known as fluorescence. It is quite common, instead of drawing atoms all the time, to instead represent these orbits with horizontal lines. These are the possible energy levels of each electron. The lowest possible energy level for an electron is known as the ground state. Any levels above this level are called excited states. The concept of fluorescence is explained as follows. A light wave with energy above that of the visible spectrum, for example ultraviolet light, is shone on the material. If the light wave has that specific precise value that is needed for that electron to jump an energy level or many energy levels, it will be absorbed, as I've shown here. Here in this case, this light wave had the exact energy such that when the electron absorbed it, that electron jumped 3 energy levels. Typically, an electron in an excited state such as this is unstable. That is, it has a tendency to want to go back to its ground state. However, the key to fluorescence is that that electron does not have to go back to the ground state in one step. For example, in this case, the electron goes from that third excited state instead first to the first excited state, thereby emitting a light wave. Then, eventually, that electron will also jump from that first excited state back to the ground state, emitting another electron. Overall, what happened in this scenario was a light wave of high energy, in this case a UV light ray, was absorbed by the material, which in turn caused the emission of 2 light waves of lower energy, one or both of which could have the energy associated with light waves in the visible spectrum. This is what fluorescence is. Fluorescence is the absorption of light waves with energies above that of light in the visible spectrum, and then the emission of light waves of lower energy in the visible spectrum. This is why objects that undergo fluorescence appear to glow. So far in this video, I've focused my discussion on electrons. For the remainder of this video, I will instead turn my focus to the other part of the atom, namely the nucleus. As the nucleus is composed of both protons and neutrons, it should be intuitively safe to say that the mass of the nucleus is equal to the sum of the masses of the protons and the neutrons within it. However, it turns out this is not in fact the case. The mass of the nucleus is in fact slightly smaller than this value. This difference is known as the mass defect of the nucleus. It was not understood until Albert Einstein came along as to why the mass defect existed. Of course, I assume you all know the very famous equation E equals mc squared, and what this equation tells us is that energy is equivalent to mass. Mass can be converted into energy and vice versa. This mass defect is therefore a result of mass that has been converted into energy. Inside the nucleus, protons and neutrons are attracted to each other by what is known as the strong nuclear force. We know from our discussion on charges that like charges repel and unlike charges attract. Therefore, straight away we can wonder, how is it the case that there can be more than one proton in a nucleus? All protons, of course, have a positive charge, and therefore they should be repelling each other. What keeps the protons and neutrons together in the nucleus is what is known as the strong nuclear force. It turns out that the strong nuclear force is much greater than this electromagnetic force associated with charged particles that tries to repel the protons from each other. This bound system of neutrons and protons is at a lower energy level than the unbound constituents. This difference in energy is what is known as the binding energy of that nucleus. It is, if you like, the minimum energy needed if we wish to separate that nucleus into the constituent protons and neutrons. As an aside, allow me to quickly summarize the 4 fundamental forces in nature. As I just stated, the strong nuclear force is the force which holds the nucleus together. As you may have guessed by the name, it is the strongest of the 4 fundamental forces. It also, however, only acts over very small distances. This is why we do not see the strong nuclear force outside the study of atomic physics. Again, as I also already stated, the electromagnetic force is the force associated with charged particles. It's the force that causes like charges to accelerate away from each other and unlike charges to accelerate towards each other. This force is also roughly 1% as strong as the strong nuclear force. It is because of this that the nucleus can exist at all. Also, as we know, this electromagnetic force is governed in the case of 2 simple charges by Coulomb's law. In that case, we know that the force between 2 charged particles is inversely proportional to the square of the distance between them. Hence, although the electromagnetic force decreases with increasing separation of the charges, the range is in fact infinite. The separation between them, that value of or, can take any value in Coulomb's law. The 3rd strongest fundamental force is known as the weak nuclear force. For the most part, the weak nuclear force is outside the scope of the MCAT, but one of its functions is to increase the stability of the nucleus. It does so by causing what will be the main topic in the rest of this video, namely radioactive decay. This force is roughly 1/1,000,000th as strong as the strong nuclear force, thereby justifying its name. However, also by its name, it is a nuclear force, and it also only acts at the atomic and nuclear scale, just like the strong nuclear force. The final fundamental force, and the one you are probably most familiar with, is that of gravity. Gravity is the fundamental force that causes an attraction between 2 different objects due to their masses. In our minds, we may think of gravity as being a very strong force. It of course keeps our feet on the ground and also causes the Earth to orbit the Sun. However, in the case of us on the Earth, of course the Earth is very heavy and the distance between us and the Earth is very small. Likewise, for the Earth going around the Sun, both of those objects have a very large mass. If we were to instead consider the gravitational forces between 2 atoms, they would be very small if not negligible compared to the other 3 fundamental forces. In fact, compared to the strong nuclear force, the strength of the gravitational force is roughly 10 to the power of minus 40 times that of that force. Finally, likewise with the electromagnetic force, the gravitational force between 2 objects of different masses is inversely proportional to the square of the separation between them. Therefore, again, as this value of separation can be any value, the range of the gravitational force is infinite. Up to this point in this video, I have focused on the electrons in the atom. For the remainder of this video, I will instead look at the nucleus. In particular, I will focus on what happens when we either combine nuclei or split nuclei. As this will involve the changing of the number of particles within the nucleus, I would like to briefly recap what I'm sure you already know about isotopic notation. Of course, it is the number of protons and therefore also the number of electrons that determine a particular element. An isotope of a particular element is one that has the same number of protons and electrons of that element, but has a different number of neutrons. The notation we use to represent a particular element or isotope is as follows. We begin by using a large letter or letters to represent a particular element. For example, capital H is used to represent the first element of the periodic table, namely hydrogen, and capital H small e is used to represent helium, the second element, and so on. Here I've used capital X as a variable for any possible element. The number of protons in that element or isotope is represented by capital Z. Capital C is typically placed in the bottom left-hand corner and is known as the atomic number. The mass number capital A of that element is then written in the top left-hand corner. The mass number of an element is equal to the number of neutrons plus the number of protons. The reason we do not include the number of electrons in the mass number is because the mass of the electron is much less than the mass of the neutron and the proton. As we shall see in the next few slides, in a nuclear reaction, it is important to balance the number of nucleons, that is, the number of protons and neutrons, by balancing both the atomic number and the mass number. First, let us begin by considering what happens when nuclei combine. This is what is known as nuclear fusion. For example, in our own Sun, hydrogen nuclei are fused together to form helium nuclei. As I've shown here, we have two hydrogen nuclei combining to create one helium nuclei. In this fusion process, energy is also released. In the case of the Sun, a large portion of this released energy is what we get in the form of heat and light. This is, however, a simplified version of what actually happens on the Sun. On the Sun instead, a total of 4 hydrogen nuclei are used to create one helium-4 nucleus. The energy released in such a process is again partly in the form of light and heat, but also in the form of other particles like neutrinos. Nuclear reactors on the Earth are typically not of this type. This is because in order to make two nuclei combine together, a large amount of energy is needed. In the Sun, this is easily achieved as the Sun is very large. There is a large gravitational force that can overcome the natural repulsion between two hydrogen nuclei. However, nuclear reactors on Earth do not have this same benefit, and therefore instead, nuclear reactors on Earth typically undergo instead what is known as nuclear fission. Contrary to nuclear fusion, nuclear fission is instead the breaking up of a large nucleus into smaller nuclei. One of the most studied and used nuclear fission reactions is that of uranium-235 and a neutron. This is because when they combine, as I've shown here, an unstable isotope, uranium-236, is formed, which quickly decays into barium-141, krypton-92, 3 neutrons, and again, excess energy. Why is this an important fission reaction? Well, if you look to the left before the reaction occurred, we initially had 1 neutron. After the reaction, we now have 3 neutrons. Then if we have a container that contains many uranium-235 nuclei, then simply adding 1 neutron into that container will create 3 neutrons in one reaction. Now we have 3 neutrons which can interact with 3 different uranium-235 nuclei, creating 9 nuclei, and so on. There is a chain reaction with energy released each time. This is one of many reasons why it is typically nuclear fission that occurs in a nuclear reactor on Earth. As I just stated, the isotope uranium-236 is naturally unstable. Such unstable nuclei will typically decay naturally. This is what is known as radioactive decay. Radioactive decay is the spontaneous decay of an unstable nucleus into a lighter one. releasing some form of radiation in the process. In terms of our isotopic notation, this is what generally happens with radioactive decay. We have an unstable nucleus X with a mass number A and an atomic number Z, which then undergoes radioactive decay, potentially changing the element and the atomic and mass numbers. Also, some form of decay particle or particles are released in the process. For the MCAT, 3 different types of radioactive decay can come up. The first type of decay is known as alpha decay. In alpha decay, as its name suggests, an alpha particle is released. An alpha particle is, if you like, a helium nucleus. It is composed of 2 protons and 2 neutrons. As it has this form, this is how the isotope changes when it undergoes alpha decay. Assume again we have our original unstable nuclei that now undergoes alpha decay. As it is emitting a particle which has 2 protons, that isotope is going to lose 2 protons. Therefore, its atomic number, which is the number of protons, is going to decrease by 2. Z has changed to Z-2. Remembering that the mass number is equal to the number of protons plus the number of neutrons, then the mass number will decrease by 4. By 4 because 2 neutrons and 2 protons have been released. Remember, since an element is defined by how many protons it has, since we have changed the number of protons here, we have also changed the element. I have represented this by changing the element letter from X to Y. Again, this nuclei has been created because an alpha particle was released. Therefore, we must also have an alpha particle on the right. As an alpha particle has 2 protons, its Z is simply going to be 2, and its mass number will be 4. 4 again because it has 2 protons and 2 neutrons. Finally, as it is an alpha particle, we use the Greek letter alpha to represent it. As an example, let us return to our friend uranium-238. What happens to this isotope when it undergoes alpha decay? Well, as we see from above, it must lose 2 protons and lose 2 neutrons, thereby causing its atomic number to decrease by 2 and its mass number to decrease by 4. Since uranium by its definition has 92 protons, this new element will now have 2 less protons, in other words, 90 protons. Looking up in the periodic table what element has 90 protons, we know that this new nuclei must be thorium. Also again, as the mass number has decreased by 4, this is thorium-234. Finally, as always with alpha decay, we must have also created an alpha particle as I've shown here. As we shall see after looking at the other 2 possible radioactive decay processes, alpha particles being composed of 2 neutrons and 2 protons are relatively very heavy. As they are so large and heavy, they easily interact with matter. This therefore means that if we wish to protect ourselves from alpha radiation, not much shielding is needed. In fact, simply placing a sheet of paper between your body and particles undergoing alpha decay is good enough to stop alpha radiation from hitting your body. This is, however, not true for the next type of radioactive process known as beta decay. Just as with alpha decay, in beta decay, a beta particle is emitted. A beta particle is simply a high-energy electron. Note also that it can be the antimatter version of an electron, in other words, a positron. A positron is a particle that is the same as an electron in every way except for its charge. Whereas the relative charge of an electron is -1, the charge of a positron is +1. This means that, if you like, we can break up beta decay into 2 different branches. These branches are known as beta plus and beta minus decay. Beta minus when an electron is emitted, and beta plus when a positron is emitted. It's important to note here that this is still a nuclear reaction. This is still entirely to do with the nucleus. This is because this is not simply an electron in a shell being ejected from that atom. Instead, what is happening is a neutron is decaying into a proton and a beta particle, a proton and an electron. This is how this is still a nuclear process. To understand what happens to the unstable nuclei, let us look at beta plus and beta minus decay separately. First, remember, beta minus decay is the emission of an electron. In beta minus decay, a neutron is converted into a proton and a beta minus particle. Since this beta minus particle is released, in terms of the remaining nucleus, a proton has changed into a neutron. Therefore, the number of protons and therefore the atomic number has increased by 1, but the mass number has stayed the same. Remember, the mass number is the number of protons plus number of neutrons. If a proton changes into a neutron, we still have the same mass number. Therefore, for beta minus decay, all that happens is the atomic number increases by 1 and a beta minus particle is emitted. Likewise, for beta plus decay, a proton is instead converted into a neutron and a beta plus particle. Therefore, rather than having a neutron turn into a proton, we now have a proton turning into a neutron. Hence, we now have one less proton and therefore the atomic number has decreased by 1. Again, as with beta minus decay, the mass number has stayed the same. The number of protons plus the number of neutrons has not changed. Hence, in this case, we simply have the atomic number decreasing by 1 and a beta plus particle emitted. As a beta particle is simply an electron or a proton, it is much lighter than an alpha particle. This means that beta particles are more susceptible to passing through materials. If we had the same shielding as we did before, a simple sheet of paper, those beta particles would pass through that paper into our body. Instead, we now need a tougher form of shielding, for example, something like aluminum. If we replace our paper with aluminum, that aluminum sheet will not allow those beta particles to pass through it, thereby entering our bodies. The final type of radioactive decay that can come up on the MCAT is that of gamma decay. Gamma decay is simply the emission of gamma rays. If you recall from our discussion of the electromagnetic spectrum, gamma rays are simply a form of light wave, a form of electromagnetic wave. Also recall that gamma rays had the highest frequency. As the energy of a wave is directly proportional to its frequency, remember E is equal to hf, gamma rays are the portion of the electromagnetic spectrum that have the most energy. Of course, also, as gamma rays are simply a form of electromagnetic wave, they have no charge. This therefore means that the emission of a gamma ray is not going to change either the atomic or mass number of the nucleus. All that gamma decay causes is a reduction in energy of an unstable energetic nucleus. In order to represent the fact that the original nucleus is energetic, I've used an asterisk to distinguish it from the lower energy resulting nucleus. Also, as the atomic number Z has not changed, then the type of element has not changed. For example, if we initially had uranium, we still have uranium after gamma decay. Both the atomic number and the mass number have not changed. All that has happened is that unstable energetic nucleus has released some of its energy, represented here by the removal of this asterisk, and a gamma ray, represented by the Greek letter gamma, has been released. Of course, as light has no mass associated with it, and as gamma rays are very energetic forms of electromagnetic waves, they are going to penetrate through material even better than alpha and beta particles. Therefore, even in the case of having an aluminum sheet between us and the unstable nuclei, gamma rays will pass through that sheet. We instead need an even better shield if we are to protect ourselves from gamma radiation. Common examples of such shielding are thick layers of either lead or concrete. They must be thick because gamma rays can even pass through thin layers of such materials. Before moving on, let us recall an important fact about radioactive decay. Radioactive decay is spontaneous. This means that we cannot predict with certainty when a particular nuclei will decay. The best we can do is say that after a certain amount of time, a certain portion of a sample of nuclei is expected to decay. To quantify this, we introduce what is known as half-life. If we have a sample of radioactive particles, the half-life of that sample is defined as the time it takes for half of that sample to decay. For example, if we have 500 radioactive particles and 250 of them have decayed after 20 minutes, then the half-life of that sample is 20 minutes. In science and on the MCAT, we represent half-life by capital T sub a half. As the range of half-lives is very broad, some half-lives are measured in milliseconds, whereas others can be measured in hours, days, weeks, even years. Half-life is, again, another example of an intrinsic property. For example, the half-life of lithium-8 is as low as 0.8 seconds. In the other extreme, the half-life of uranium-235 is 700 million years. We can therefore wonder, if we are given a sample of a known radioactive substance, thereby knowing its half-life, as well as knowing the number of particles in that sample initially, in other words, the number of particles that have not decayed, we can ask how many undecayed particles are left after a particular time t. How do we work this out? This is in fact calculated using what is known as the radioactive decay equation, which I will derive for you here. Let us assume that we have a given sample and let n represent the number of nuclei in that sample that have not decayed at a time t. It turns out that the rate at which these nuclei decay is directly proportional to the number of undecayed nuclei that remain. That is, the rate of change of undecayed nuclei, in other words delta n over delta t, is directly proportional to the number of undecayed nuclei. In a sense, this means that the more undecayed particles there are, the more that will eventually undergo decay. As this is a direct proportionality relation, I can replace this proportionality sign with an equal sign as long as I include a constant. Here I've called this constant minus lambda. Minus simply because if I had left it as a plus, then all of the values of these lambdas, as we shall see shortly, would have ended up being negative. In order not to have negative signs all the time, I have instead placed one negative sign here in this equation, which I am free to do. Some of you may or may not feel comfortable solving this equation for n. Don't worry if you can't, it is outside the scope of the MCAT. What happens is, however, these deltas are replaced by differentials. We allow these changes to tend towards 0 and then solve the resulting differential equation. Doing so results in the exponential decay equation. And here I've replaced small m by capital N just so you are aware of the fact that sometimes you will see one or the other, n or capital N. The equation states that the number of undecayed particles at a time t, this capital N, is equal to the number of decayed particles at some defined t is equal to 0 time, in other words initially, multiplied by the exponential of minus this constant multiplied by the time t. This constant lambda is known as the decay constant, or you may also sometimes see the disintegration constant. What this equation is telling us is that naturally radioactive substances decay exponentially, as I've shown on this graph. With increasing time, there is less particles that can decay as more and more of the particles in the sample have already decayed. Also, it is apparent from this graph that more particles decay initially compared to at later times. Again, this is because there are more undecayed particles in the sample initially. Remember, however, my initial question was, how do we calculate the number of particles at a time t if we know both the number of initial undecayed particles, this n sub 0, and the half-life? However, while this equation does have this n sub 0, it does not have the half-life in it. It instead has a different constant known as the decay constant. This decay constant, however, is in fact directly related to the half-life. The decay constant is equal to the natural log of 2 divided by the half-life. I will leave it in your own time to derive this relationship, but it can be derived by simply looking at the exponential decay equation. When the time t in that equation is the half-life, then half of the particles have decayed. This means that n over n sub 0 is a half. This equation can then be solved to give the relation that I have here. Thus, it is now possible to calculate the number of undecayed particles at a particular time t if, given the number of undecayed particles initially at some time t is equal to 0, in other words n sub 0, and the half-life of that radioactive substance. This is, in fact, a very common question on the MCAT. I would now like to finish this video by slightly diverging. I would like to briefly discuss something that I probably should have brought up in a previous video, namely mass spectrometry. Mass spectrometry is a method of calculating the charge-to-mass ratio of a particular ion or charged particle. It does so by measuring how much that charged particle is deflected in a magnetic field. If you recall from our study of magnetic fields, a charged particle placed in a constant magnetic field will move in a circle. The radius of that circle is actually equal to the mass of that charged particle multiplied by that particle's speed divided by both the charge of that particle and the magnetic field strength. This equation can then be used to calculate the charge-to-mass ratio. The setup for this is as I've shown here. A particle or a stream of particles enters a container as shown. Partway through this container is a permanent magnet. As I just described, as this particle enters the resulting magnetic field, it will tend to want to curve into a circle. Therefore, it will either curve to the left or to the right, depending on whether that charge is positively or negatively charged. Where that particle actually hits the wall can be determined, thereby allowing us to calculate the radius of the resulting circle that that particle would move in if that wall wasn't there. If we also know the speed at which those particles enter that tube, as well as the strength of the magnetic field from the magnet, we can then use that equation for the radius to calculate the charge-to-mass ratio of that particle. Hence, naturally, if we also know either the charge or the mass of that particle, we can use this known ratio to calculate the other. This idea can then be used with more complicated mixtures to determine the chemical structure of such mixtures. Before moving on to our last video, as always, let us now recap what we have learned so far about atomic and nuclear physics by looking at questions of a similar style to the MCAT. This first question is checking that we understand what is meant by fluorescence. The question asks which wave property changes when a wave undergoes fluorescence. Is it the wave's wavelength, its speed, its intensity, or its polarization? Well, let's recall what fluorescence is. Initially, a wave that has a large energy, for example that of ultraviolet light, is shone onto an object. As this object has very high energy, it also has a very high frequency and a very small wavelength. This wave can then be absorbed by the atom, causing an electron to jump from a lower energy level to a higher energy level. Once in this higher energy level, that electron will be unstable, eventually returning to its original energy level. However, the important thing about fluorescence is it does not have to do this in one step. It can drop from this very high energy level to first another high energy level, albeit a bit lower. Then from there it may drop to another excited energy level or back to its original level. In each drop, a light wave is emitted. As energy has to be conserved, if multiple light waves are emitted, they must each have less energy than the light wave that was absorbed. As they have less energy, they also have a lower frequency and a larger wavelength. Thus, we see that it is in fact the wavelength of the light that has changed. Therefore, the correct answer here is option A. Next, we have a question which is dealing with the 3 types of radioactive decay that you need to know for the MCAT. It asks, in which of the following radioactive decay processes does the atomic number not change? Is it alpha, beta, or gamma decay, or is it the case that the atomic number changes in all 3 cases? To begin, let's recall what is meant by the atomic number. The atomic number Z of a particular element or isotope is simply equal to the number of protons in that element. In alpha decay, an alpha particle, which is simply a helium nucleus, is released. An alpha particle contains 2 protons and 2 neutrons, and therefore the atomic number decreases by 2. Therefore, the correct answer cannot be option A. Beta decay is the release of a beta particle. As I discussed, a beta particle can either be an electron or its antimatter equivalent, a positron. One may naively assume, therefore, that the atomic number does not change. Remember, the atomic number is the number of protons, therefore if it is an electron that is emitted, one would think that the atomic number does not change. However, remember, we are dealing with nuclear physics. Radioactive decay has nothing to do with the electrons orbiting the nucleus. This electron instead came from a neutron decaying into both a proton and an electron. This proton remains in the new nucleus and the electron is ejected. Therefore, we see that we have increased the proton number by 1 in the case of beta minus decay. In the case of beta plus decay, on the other hand, a proton is changed into a neutron and a positron. Therefore, in beta plus decay, the proton number decreases by 1. In either case, the proton number changes and therefore the atomic number changes. Therefore, the correct answer cannot be option B. The final type of decay you need to know is that of gamma decay. Gamma decay is simply the release of a gamma ray, a form of electromagnetic wave. As it is a form of light, it does not have any charge associated with it, and therefore the release of a gamma ray simply reduces the energy of the nucleus. Hence, in this case, as there has been no change in the proton number, the atomic number Z has stayed the same. Thus, the correct answer here is option C. Half-life is now considered in this next question. If the half-life of a particular isotope is X, what fraction of a sample of that isotope will remain after 4x years? Is it x over 4, 8 over x, 1 over 16, or 1 over 32x? There are many ways to approach this question. I'm going to do it in steps. We know that the half-life of this isotope is x years, and therefore remembering what half-life means, this means that after x years, half of that sample will have decayed. What about after 2x years? What happens if we look at the sample after 2 half-lives? We know after 1 half-life, in other words x years, half of that sample will have not decayed. This means that after another half-life, after 2 half-lives, there will now only be half of that half undecayed. In other words, a half multiplied by a half, in other words, a quarter of those particles are now undecayed. Likewise, we can again consider after 3 half-lives, after 3x years, and we will now have a half multiplied by a half multiplied by a half. That is, an eighth of the particles will now be undecayed. Finally, after 4 half-lives, after 4x years, what we're looking for, we are now left with a half multiplied by a half multiplied by a half multiplied by a half. That is, the fraction of the sample that has not decayed is a half to the 4, in other words 1 over 16. Thus we see that the correct answer is option C. Our final question is to do with the photoelectric effect. We are told that light of frequency 5 multiplied by 10 to the 12 Hz is incident upon iron, and we are also told that iron has a work function capital W of 4.7 electron volts. We are then asked, what is the minimum kinetic energy of the ejected electrons? Is it 3.3 multiplied by 10 to the minus 21 joules, 7.52 multiplied by 10 to the minus 19 joules, 7.49 multiplied by 10 to the minus 19 joules, or are no electrons ejected? Again, to answer this question, let us recall what is meant by the photoelectric effect. When light with energy E is equal to hf is incident upon a metal, that light can cause electrons to be ejected from the surface of that metal as long as the energy of that light is above the work function of that particular metal. Remember, the work function of the material is the energy needed to liberate the electrons. The electrons are of course chemically bound in some way to the metal, so therefore energy is needed if those electrons are to be ejected. Any remaining energy left over from the light then goes into the kinetic energy of the ejected electrons. To begin, therefore, we need to check that the energy of the light is greater than the work function of the metal, which is iron in this case. What are we told in the question? Well, we are told that the frequency of the light F is 5 multiplied by 10 to the 12 Hz, and we are also told the work function of iron in electron volts. It is 4.7 electron volts. As we are going to calculate the energy of light in joules, we must first convert this energy, this work function, into joules. Remembering that 1 electron volt is roughly defined as 1.6 multiplied by 10 to the minus 19 joules, we can convert this energy value into joules, giving us 7.52 multiplied by 10 to the minus 19 joules. Thus, if electrons are to be ejected, the energy of the light must be greater than this value, greater than 7.52 multiplied by 10 to the minus 19 joules. Let's check if this is in fact the case. The energy of a light wave, remember, of a particular frequency f is simply Planck's constant multiplied by that frequency. It is simply h, which is roughly 6.6 multiplied by 10 to the minus 34, multiplied by the frequency of the light, which in this case is 5 multiplied by 10 to the 12. Working this out, we get that the energy of this light wave is 3.3 multiplied by 10 to the minus 21 joules. Comparing this to the work function of the iron of the material, we see that the energy of the light wave is much less than the work function of the iron. Because of this, we therefore know that no electrons are going to be ejected. This does not impart enough energy into the electrons in order for them to overcome their chemical bonds to the metal. Thus, the correct answer here is option D. No electrons are ejected. Before moving on to our second and final video on atomic and nuclear physics, let us briefly recap what we learned so far. As we just saw in the last question, I began by talking about what is known as the photoelectric effect. This effect is the ejection of electrons from a metal due to light incident on that metal, transferring its energy to the electrons. As I emphasized in the last question, in order for electrons to in fact be ejected, the energy of the incident light must be greater than the work function of the metal. Rather than talking about a minimum energy needed to eject electrons in the work function, we can also talk about the minimum frequency needed. This is known as the threshold frequency. The work function is then related to this threshold frequency simply by W is equal to hf. The work function is equal to Planck's constant multiplied by the threshold frequency. I then discussed in detail the Bohr model of the atom in relation to electron energy levels. Electrons cannot exist anywhere in an atom, they can only exist in particular discrete orbits. If they wish to jump from a lower energy orbit to a higher energy orbit, a light wave of a specific frequency and therefore energy must be absorbed. In the opposite sense, if an electron wants to jump down from a high energy level to a lower energy level, it must emit a light wave. I then described how certain objects seem to glow due to what is known as fluorescence. Fluorescence is the absorption of light waves of a certain wavelength with the emission of light waves of different wavelengths. The binding energy of a nucleus was then considered, which is simply the minimum energy needed to separate that nucleus into its constituent particles. I then briefly described the four fundamental forces, describing how strong each is relative to the others. I also stated that there is a difference between the sum of the masses of the constituent particles within a nucleus and the mass of the nucleus itself. This is known as mass defect. The fusing and splitting of nuclei was then considered in nuclear fusion and nuclear fission respectively. As nuclear fusion requires a lot of energy, it is not typically observed in nuclear reactors on Earth, but is seen in, for example, stars. Nuclear fission, the splitting up of nuclei, is instead what is typically used in nuclear reactors. The spontaneous decay of certain unstable nuclei, namely radioactive decay, was then considered. For the MCAT, 3 different decay particles must be known. The first and the heaviest of the particles is an alpha particle. An alpha particle consists of 2 protons and 2 neutrons, thereby reducing both the atomic and mass numbers of that nucleus when the alpha particle is emitted. Beta decay is instead the release of a beta particle, which could be either a high energy electron or a positron. As in such decay, either a neutron is replaced by a proton or vice versa, the atomic number of the nucleus changes, but the mass number remains the same. The final type of decay is known as gamma decay and is simply the emission of a gamma ray, a high energy form of electromagnetic wave. As a gamma ray is not a particle in itself and has no charge associated with it, the atomic and mass numbers stay the same. The release of a gamma ray simply lowers the energy of the unstable nucleus. In order to quantify how fast a particular isotope is at decaying, the concept of half-life was introduced. For a given sample, the half-life of that sample is simply the time it takes for half of the particles to decay. I also derived for a given sample what the number of decayed particles is expected to be at a later time t. This was done using what is known as the radioactive decay equation. I then finished this video with a brief tangent on mass spectrometry. This analysis technique is used to measure the charge to mass ratio of a particular substance. This is done by measuring the deflection of particles within that substance in a magnetic field. If, for example, the particle charge is known, this technique can be used to measure the masses of individual constituents of a sample. This now wraps up our penultimate video and our first of 2 videos on atomic and nuclear physics. In the next and final video, I will go into more detail about the electronic structure of the atom, as well as give a brief introduction to various quantum physics topics that you must know for the MCAT. As always, I hope this video has been useful to you, and I shall see you guys in the next one.